Hi there YouTube, my name is Nico and welcome back to my channel. In this video, we're going to look at sound resonance. If you missed my previous video on how sound actually works, please click the link up here and it will take you to that video. Is it possible to actually break a glass with sound? So let's get into it. I hope you have your science hat on. Every object is made of matter. Thus, everything in the universe. All those objects consist of atoms and molecules, which will vibrate at a specific frequency. This is known as its natural frequency or the resonant frequency. Now, if we go back to our previous video, we talked about how the frequency is the number of cycles in 1 second. So if you look at this sine wave over here on the screen, there's one cycle over there, and if I have multiple cycles, that will be its frequency measured in hertz. When there is an earthquake, the ground vibrations will happen at a specific frequency. Some of that energy is converted into kinetic energy or motion energy if you want. If that frequency is the same as the frequency of an object, let's say for instance a building wall, that wall will be affected by the motions caused by the earthquake, as you can see in this picture. The question now is, can we apply that same principle, but with audio as the vibrations and a wine glass as the object? Because of science. So let's look at the properties of a wine glass. The resonant frequency of this glass can be measured using a microphone and an app. By simply tapping the glass with an object, like the teaspoon for instance, you will hear that ringing sound. That ringing sound is its natural frequency. And interestingly enough, if I tap the glass very softly or much harder, the frequency of the sound will still be the same. I measured a frequency of 594 Hz. That is now indicated by the blue wave on the screen. So that means that there is 594 cycles in 1 second. Now, if we can generate that same frequency of 594 Hz at an amplitude loud enough, we might be able to affect the structure of the glass. We can generate a sweeping audio tone that will start at a chosen frequency and slowly change to a stop frequency. This will just help us just in case the measurement was slightly off or wrong. If we now expose our glass to this outside frequency, indicated by the green wave, what is actually going to happen? Well, there are two options. The frequency of the glass and the outside frequency is either going to be 1, in phase, or 2, out of phase. Now, what do we mean by that? Let's start with out of phase. If the two frequencies are the same, but they are out of phase, they don't match up in terms of time. If I overlay the glass and the audio frequencies on top of each other, we will see that the two frequencies do not match up perfectly. Mathematically, you can actually add these waves together. And you will see on the top end of the curve is the positive side and the bottom end is the negative side. If the resulting wave is bigger than the original wave, it is then called constructive. But where the resulting wave is smaller than the original, it is destructive. Especially where the green wave is on the negative side and the blue wave is on the positive side, or vice versa. For example, if the blue wave has an amplitude of 85 decibels and the green wave has an amplitude of minus 20 decibels, the resulting wave would be 65 decibels. So you see, it has actually destroyed the original wave, which is why it's called destructive. The areas highlighted will either be bigger than the original wave, or constructive, or it will be smaller than the original wave, or destructive. However, the second scenario that we have is what would happen if the two frequencies are exactly the same and they are in phase, or other words, they match up perfectly. Mathematically, again, we can add these two waves together, but the result is going to be double. It's going to be much bigger than the original waves, which is symbolized by the red wave on the screen right now. If the amplitude of the new wave is big enough and it exceeds the strength of the glass will actually break. For example, remember that our blue wave and our green waves have a maximum amplitude of 100 decibels. That means that the resulting wave would now actually be 200 decibels, which is constructive. An example of what would happen if I expose a glass to a frequency that matches its resonant frequency can be seen in the pictures. Here is the example of the experiment. A loudspeaker is pressed right against the glass, and if the frequency generated by the loudspeaker is the same as the glass, it will actually shatter the glass. Now, I know at this stage you might be thinking, well, Nico, why didn't you actually do this experiment? Well, I did, and this is my results. Now, as you can see, unfortunately, during my experiment, my loudspeaker was just simply not powerful enough. I need to get another speaker to be able to do this experiment properly. And seeing that South Africa is on a 21-day lockdown at this stage, I am not going anywhere to get that loudspeaker. So, guys, sorry about that. We'll have to postpone me breaking the glass. Another fact to keep in mind is the harmonics. This is effectively an integer factor of the original frequency. For example, if I look at the blue wave, which has a frequency of, for instance, 100 Hz, which is one factor, then the first harmonic would be 200 Hz, which is now the green wave. So, the original wave frequency plus the number of the harmonic times the original frequency. So, the first harmonic would be 100 Hz plus 1 times 100 Hz equals a total of 200 Hz. The second harmonic would be 300 Hz. That means that I can fit in 3 waves in place of 1 wave. So that would be the original wave plus the number of harmonic times the original frequency, which is 100 Hz in this case, plus 200 Hz, which equals 300 Hz in total, and so forth and so forth. Effectively, you can take your harmonic frequency and you can divide it by the original frequency and get a full integer. Another interesting thing about the harmonic frequencies is that it will contribute to the movement or breaking of the glass. But if you go back to my previous video, you will remember that we mentioned that the higher the frequency, the quicker the wave will attenuate. Thus, the effect on the glass will be way less than the lower frequency. And just for fun, in music theory, a doubling of the bass frequency is actually an octave, which is 12 semitones. For example, if I take C1 on a piano, which has a bass frequency of 32.7 Hz, if I double that, that will be C2 on a piano. And that will have a frequency of 65.41, which is double the original frequency. Then if I double C2's frequency, you will see it goes up to 130.81 Hz. And so forth and so forth. This accounts for the fact that our ears like to hear those frequencies together. They complement each other by also being harmonics of the original frequency of C0, which is 16.35 Hz. Similarly, we would expect that a C major 3-key chord might have frequencies that have something in common. That chord consists of, for instance, C2, E2, and G2. It's also sometimes called the 1-4-7 chord. Each semitone will get incrementally bigger than the previous one. It can be graphed out on a logarithmic graph with the log base of 12. For example, C2 on a piano has a frequency of 65.41. C sharp has a frequency of 69.30 Hz. And then D has a frequency of 73.42. And D sharp 77.78, and so forth and so forth. And if I look at those frequencies, you will see that there isn't an increment between them that is constant. The increment starts getting bigger as you go higher and higher and higher. Okay guys, I hope you learned something new today. We are going to hopefully continue this series later on, and I will definitely show you how to break the glass with sound. Of course, thank you very much for watching this video. If you haven't yet, please press the subscribe button and the like button and leave me a comment in the section down below. And I will see you guys in the next video. Cheers for now.